Hello. Today we're going to talk about linear time invariant systems. Linear time invariant systems have two properties. They're linear, and we'll talk about what that means in a minute. And they're time invariant. And in a nutshell, that means that they operate the same yesterday, today, and forever. So let's start with what linearity means for LTI systems. So a system is linear if and only if t, which represents the operation of the system, operating on A times one signal plus B times another signal gives the same result as A operating on the first signal plus B times the system operating on the second signal. In other words, if we combine the two signals and operate on them as a package, it's just the same as if we operated on each of the signals individually and then recombined them. We'll go through some examples so you can see where this how this works and get some intuition for it. A system is time invariant if and only if when if we take a signal, actually I won't even do the subscripts because it's the same one. If we take a signal x delay is equal to x n minus nd, then we have that y delay is equal to y n minus nd, where yd is the output of our system operating on xd, and y is the output of our system operating on x. Okay, so this one, in my experience, it's a little bit harder to get your head around exactly what's going on with this particular property. So let me explain it in words, and then we'll go through some examples. If we have a system that operates on, say, a signal, produces its output, then it's saying if we were to come along later, process that signal at a later point in time, so that's the delayed signal we're talking about, we would get the same output as if we had processed it earlier, except that we get the output of the delayed signal delayed by the same amount. So, but more intuitively, a time invariant system is one that works the same yesterday, today, and forever. So a system is LTI, linear and time invariant, if both properties hold. Okay, there are other properties of LTI systems that are kind of special cases. So far we have just two properties that have to hold to give us an LTI system. But an LTI system could also have these other properties. And the first one is causality. Causality is what makes a lot of science fiction movies well, a lot of science fiction movies aren't causal. But that's okay. A system is causal if and only if y of n, which is some system t operating on x. We're keeping the system very generic right now and not specifying what that operation is, just that there is some system that operates on x to give us an output. So it's causal if it depends, if the output y depends only on, let's see, x of k for k less than or equal to n. So this means that the output can only depend on what we've seen so far and not on something in the future. Next, stability. Stability is actually defined in multiple different ways, and they're all similar most of the time. But there are cases where one definition of stability might apply and others don't. So we're going to talk about what we call bibostable. It stands for bounded in, bounded out. So if every bounded input produces a bounded output, and mathematically that can be expressed as when xn is less than some bound on b, which is less than infinity, for every n, then yn is less than another bound, doesn't have to be the same one, that's less than by, also for every n. An example of something that is not bibo would be yn is equal to the sum from k equals 0 to n, k, of x of k. So why would that be not bibo stable? Well, assume that x is equal to 1. So that's fine. By the way, we can have, depending on the definitions, a less than or equal there. So we'll just say x is equal to 1, so bx is 1. That's less than infinity, so the first condition holds. The second one, y of n, well, y is going to be just equal to, y of n is going to be equal to n, because as we, or n plus 1, because we start at 0. So as n grows toward infinity, y of n will grow towards infinity and will not be bounded. So this one is not bibo stable. So one last property we want to cover here on these bonus properties is memoryless. And as I get older, I start to wonder if I'm approaching this type of a system. But thankfully not entirely yet. So a system is memoryless if y of n, which is defined as the system operating on x of n, depends only on x of n at the same value of n. Okay, so here are some examples of systems, and we can look at whether or not they are linear, time invariant, bibostable, causal, and memoryless. So the first one we'll take a look at would be y of n is equal to n times x of n. And then let's just try y of n is equal to x squared of n. And let's just do those two to start with. So we want to look at linearity, time invariance, bibostability, causality, and whether or not it's memoryless. Okay, first, linear. So we saw the definition for linearity. Right up here. The system operating on a, in this case, a linear combination. That's where you have a product and a sum. Whether or not that gives you the same output as the input. Now, in order to prove linearity, you have to show that that's true for every x. However, to disprove linearity is a lot easier. Usually, you can do the very simple thing where you say, what happens if I double the input? Does it double the output? A linear system, it would do that. A nonlinear system usually won't. Might be some edge case, but this is a really simple way to try. So let's just try that on these first two things. If I double the input here, if I had x, if where I have the x, if I put 2x, would that give me 2 times my original y? And the answer is yes. I double the input, the 2 kind of floats through, and I double the output. And it also turns out, if we go through the whole process of checking everything out, that we would find that that is indeed a linear system. Oh, let's try this in green. That looks really great. What about the next one? In this case, once again, going back to my original definition, if I choose a b equals 0 and a equals 2, then I should get that doubling of which I speak. And that's at least one test. It's not a general test, but it's something to try. But here, if I double the input and then I square it, my output is going to be quadrupled. So that is not a linear system. Time invariant. Well, if let's start with the second one, because it happens to be the easier of the two for this one. Time invariant says that things never, change. The operation of the system doesn't change with time. Well, if I square something now or square it tomorrow, it's still going to be squared. That's an easy thing to see intuitively. And sure enough, that's the way it works out. What about this other one? Is it time invariant? This is where people, I think, often second guess themselves and have the hardest time figuring out what to answer. The answer is no. So how do I get there? Well, if I were to delay the input, I would have, let's say I delayed it by 1. I would have that. If I were to delay the output, I would have n minus 1 x n minus 1. And those two aren't equal. Well, how did I know to write this correctly? Well, when we delay the input, we only impact the argument of x. And that's what we did there. We just changed the argument of x. Anything else the system imposes, we don't have any control over. We're just delaying the input. On the other hand, when we're delaying the output, let me put this here. That is the n that we substitute. We basically take every n in the whole system and we substitute it with this delayed value, n minus 1. And so we can see that the output when we've delayed the input is not the same as the output with a non-delayed input but a delayed output. And so we get the, it doesn't hold there. What about bibostability? Well, as n grows without bound, y will grow without bound. So, and it grows because we've got this factor of n in there. Well, we also know that a squaring operation can increase something dramatically. If you have a very large value, it can become extremely large. However, it may be very large, but it's still bounded. So in this particular case, we would have by is equal to bx squared. And as long as bx is finite, bx squared is finite, so we're fine with the bounds there. Causality. Are we looking at any future values of x? No, we're not. What would that look like? A future value of x would have an n plus some offset as its argument. So we're not doing that. Once again here, in fact, this one is memoryless. We only care about x at the same time. So the y only depends on the current sample and none of the rest of the signal. And although it's doing some funny things with that n out front, it only depends on the current value of n. So this is what that system would look like. All right.